Okay, I am going to walk us through the second analysis and results practice version. I am not going to answer all of the questions as some of them are very similar or the same as what are on the actual A&R. So some of them you'll have to grapple with yourself and go look up, but I will walk through how to complete the JASP portion of this. Okay, so in this scenario, we are further exploring a set of data, finger data that we've already explored in this class a little bit. So the data contains finger length data that were collected from students across different class sections. You can download the data here, and this data set includes the variables listed below. So follow the directions below to further explore this data set. So we'll go ahead and if you click and allow, it should open up the data set here. So we can see we have lab section, which lab section they're in, section 8, 9, or 10. Thumb length, the length of their thumb in millimeters. Length of pointer finger in millimeters. Middle finger length, ring finger length, pinky length, all in millimeters. Sex, and here we just have male and female. We have height in inches. Hair length in inches, so how long their hair is. Then we have a variable middle finger median split. So in this case, that middle length variable has been taken and ordered and then split in half based on where that midpoint, that median was. So we now have it split into people with shorter middle fingers and people with longer middle fingers. So short mid and long mid, depending on which group they were in. We also have height median split, which we've looked at before, done the same way where we line up those height in inches data points, find the median, and then split the data at the median. So we get the short half of the class and the tall half of the class. So your first task will be to go through and identify which of these variables are categorical in nature. So which ones are categories or groups, and which ones are quantitative in nature or are values that have meaning. Okay. So you'll go through each of these, practice that skill. And then I'd like you to continue your analysis by answering the following questions. So what do the cases in the data represent? Well, in this case, we know from the description that the data contains finger length data that were collected from students across different class sections. So each of these cases or rows in our data will represent data from one student. So in this case, our data are going to represent students. How many cases are there? Well, we can figure this out in here, and I'm going to pull this into JASP momentarily so we can see how to do that in JASP. But this is something that some people missed on the first A&R. You'll note that it says 81. However, keep in mind the first row is our variable names. So in actuality, when we take the 81 minus that one row, we will have 80 cases in this data set. Right, if I were to highlight just the cases of data, not the variable names at the top, we see 80. So we have 80 students' data represented here. Now, let's explore the variable middle length from this data set by summarizing the shape, center, and spread of the distribution, and then also the simple model. So at this point, it's going to help us to bring this data into JASP. So I'm going to start by going to File and downloading a copy of this data set. Want to open it up or save it as a comma-separated values file, a .csv file. Now, don't open it up directly from here because it's probably going to open it in Excel or some other software system. And what we really want it to do is open in JASP. So I'm going to start by opening up JASP. And then I'll open it from JASP. So open a data file. I'm going to go to my computer, and I know that my computer always downloads into the download folder, so I'm just going to go straight there. But you can browse to where yours saves. Here it is, Practice A&R 2, and I want to open that data set. So here I have it in JASP, ready to go. So once I have it in JASP, I no longer need to access it there. Okay, so first we want to look at, so we're looking at this variable, middle length, the length of middle fingers in millimeters. We want to look at the shape, the mean, and the standard deviation. So I already created the shape here, but so we can see where that comes from, we go to descriptives. We're interested in middle finger length. We see we get our descriptive statistics, including the mean and standard deviation that we need. And if I go under basic plots and click distribution plot, then you'll see where this histogram comes from. So the approximate shape of the distribution, I'm going to say that it looks, right, see if I'm, this is where it might be easier to open it in a browser where you can actually use the drawing tools. Hold on just a second. Okay, so I have opened up in a in Google Chrome so that I can use this drawing tool at the top. So fair warning, I'm really bad at drawing, especially using a mouse. So bear with me here. So we want to try to visualize what is the approximate shape of the distribution, and really we want to think about not the specific shape of our sample, but really the shape of the population that we imagine this sample comes from. So kind of if you were to blur your eyes a little and imagine it to be more curvy, and I'll do my best to kind of capture what I am seeing. Okay, so it's not too far off from normal, but it does look maybe a little bit right skewed. So in this case, maybe slightly right skewed. And it's definitely unimodal if you want to include that. But again, it's got one peak, and it looks like it's got a little longer tail to the right, which is why I'm saying it's slightly right skewed, but it doesn't look too bad. Now the mean of the distribution, this is coming from JASP here. And if you're unable to run the JASP program, you can actually open up this file here. Oh, I don't want to leave. So let me try opening it as new tab. So in this file, you will find the outputs. However, there's more than one output, so it's going to be up to you to check to see which of these is correct of the two regressions that are included and two scatter plots. So you have to determine which one to use because there are two different options, okay? But it is there. So in this case, what is the mean of our distribution? We're going with 77.05. That's coming from right here in JASP. Okay, mean. Our standard deviation is right below that, 6.765. I'm going to round. You can generally round to 2 decimal places in this class. I encourage you not to round much more than that. So 6.77. And this part is where a lot of people tend to get kind of stuck with this idea of writing out our model. So when I say put it into this modelese, that just means use that model notation that we've been talking about since classwork 8. The one that starts out like dependent variable equals constant plus effective IV plus error or residual. Um, so this is what I'm expecting you to be working on and learning. So this part is we're going to see this over and over and over again. This is what's called the general linear model. And so we're using this general linear model, this model notation, to help us to write out our model that we're working on. So in this case, we're doing the simple model, which means that right now we're only working with one variable. We don't have two variables represented. And let me make this more clear. So in this case, we are working with the simple model, which is really just the constant plus the error, because we don't have an independent variable that we're including yet, right? We're just talking about one variable. So in this case, we would write out our model as middle length equals some constant, and our best guess constant is our mean plus error. So this is really what I'm looking for here, right? We have our variable middle length in millimeters, and we're going to start with our best guess and understand that we are likely to be off probably by about 6.77. Okay. So we have our model written out here. We want to finish sketching our model out. We have the shape represented. Now I'm going to represent the mean with a vertical line. Okay. So my mean 77.05, so 75, 76, 77, it's probably right around here-ish. Right? And I want to draw a vertical line. I'm going to do my best on here. This is really like through here. And this is 77.05. That's our mean. And I'm asking you to represent your standard deviation using the a horizontal line, right? Because that represents the spread side to side around this middle point. So our spread is about 6.75. So if I am starting at 77.05 plus 6.77, so I want to go up to about 84. So probably around like here. So I can represent this as there is my standard deviation, right? And in this case, we're using 6.77 as our approximation. And this would be our approximation of our mean here. Now, what does the standard deviation of this distribution tell us? Well, it tells us that on average, these data points vary around the mean by about this much. So there is approximately 6.77 millimeters of spread on average around the mean. And you can say this a lot of different ways, but really what I'm looking for is the fact that you understand that the SD tells us the approximate average distance or spread around the mean. And in this case, it's 6.77. Now, is this simple model representing our sample of students or a greater population? And I have mentioned this previously when we started drawing. If you don't remember, you're going to want to go back and look up in classwork, I don't know, 9, I think, is where I explicitly say it. So go back and read through your notes there. And although there's variation around the mean, right, we see that there is a lot of variation. Why do we still use the mean as the basis of our model? Why is the mean generally a better model than the median in most cases? And this is going to go back to classwork, I believe 6 on central tendency. So you're going to want to go back to the very end of that classwork and look at that for help on this one. Again, it's kind of like, what's so special about the mean? Why do we use the mean so often? Why do we like the mean? What does it do for us? Now, let's try to explain the variability seen in finger length, middle finger length, right? This is the variable we've been examining by including pinky length in our model. Okay, so middle finger length, remember, is representing our DV in this case. So what is the outcome or dependent variable? That's going to be our middle finger length. And we're including pinky length in our model as the independent variable, right? That's something that we think is helping us to predict or explain the differences we see in middle finger length. So this will be pinky finger length. Now, you'll recall that we put our dependent variable when we're trying to explain or predict on our y-axis, the y-axis being the one that is vertical. And we want our independent variable, that is our x, and that's going to be on this axis. So let's see which of these has middle finger on the side y-axis and pinky on the x. So here we have pinky on the y and middle on the x. That's the opposite of what we want. Here we have middle on the y and pinky on the x. So this is the one we want, and I think actually you can check it. Now, our regression really represents that line in the center of our graph, right? It's the center, whereas the correlation is the spread. So we can see our shape here, which we'll get to again a little bit, but we can see it's a positive direction. We can see our line going through the middle here. What we want to do next is identify what is this line. So what is the regression equation that represents the line in our model? And to do this, we use this standard simple linear regression equation. And we're going to plug in the values for our B naught and our B sub 1. So let's see if I can, let me copy and paste this. Kind of, not great. So our y in this case, of course, we just said is our middle finger length is equal to B naught. So if you recall from our classwork on regression, the B naught represents in our general model, it represents our constant. That's our B naught, right? So this is the y equals B naught plus, B naught plus B sub 1, and then our independent variable is our x. Okay, so we're using the same general formatting. So the B naught is our constant, and we're going to get this from running a regression equation in JASP. So regression, and we want to do a linear regression. we want to put middle finger as our dependent variable. Pinky finger is going to be our covariate. And here is our regression output. So what we see here is we actually see two different models represented. This H sub 0 that we see here under model and down here under model, this actually represents the case where we don't have an independent variable included in our model. So this really represents what we've just done up above, right? If we look at the constant, right? The constant is what we see right here next to intercept. The constant when we don't have an independent variable in our model, H0, that's our constant, 77.05. That's our best guess. It's going to be off by a bit, and so we know that there's always going to be error. But this would be our best guess if we don't have the independent variable represented in our model. This next set right here where it says H1 and it has intercept and pinky length millimeter, this is saying, okay, now we've made a new model. We're going to call it H1. And in this model, the constant is 45.397. And we can see the effect of, right below it, the 0.571, our independent variable that we included, which was pinky length. So the value that's next to intercept is going to represent our constant. The value that's next to your independent variable represents the effect of that independent variable in our regression equation. Okay, so we need these two numbers right here. So middle finger length equals 45.397. So I'll round that a little bit. 45 point, I'll round to 40 plus, and in this case it is a plus because there's no minus sign right here, right? So if there's no minus sign, it's going to be a plus. Plus 0.57 times, right? This is my effect of, that's my B1. Now I need my X, and in this case, we know my X is the pinky length. So here is our regression equation. You could also see it written out like this. So we see our Y equal to our constant plus the effect of our independent variable. So what does this constant of 45, so I'm going to say B0 equals 45.4. So what does this represent or tell us about our research scenario? Well, we already know that this is the constant, right? This is given. This is not the answer because I already told you it's the constant. What does the constant mean for us? What does it tell us? Well, the constant represents what is the case, what is our prediction if we plug in a 0 for our X, for our independent variable. So this represents our prediction for middle finger length if pinky finger length equals 0. In other words, we would predict someone with no pinky to have a middle finger of 45.4. Right? That's our constant. That represents the case where we have 0 effect of our independent variable. In that case, we have 0x, which cancels out that second part of the equation and leaves us with just y equals the constant. Now, what does the slope B1 represent or tell us about our research scenario? Okay, so B1 in this case was the 0.57, and we know this is the slope. So when we're looking at our line, this really is the slope of our line. It's how much our line is going up for each increase that we see in X. So this tells us this represents the effect of our independent variable on the dependent variable. So if we increase x by 1, we predict an increase of 0.57 for y. So literally if we see a difference in pinky length of 1 additional millimeter, we would expect that the middle finger would be 0.57 millimeters longer, right? So it's the direct effect that we see of increasing. If we increase the pinky length, what happens to the middle finger length? It goes up by this much. Now, based on our model, what's the predicted finger length for a person with a pinky of 60 millimeters? So in this case, we're going to use our model, our regression equation that we've created or identified, and we're going to plug in for pinky length 60. So we get, let's pull up a calculator. So 60 times 0.57 gives us this part, 34.2, plus our constant, 45.4 equals 79.6. So we would predict middle length equals 79.6 millimeters. Now our spread and strength. This is going to come from running a correlation. And this is actually where we also get those scatter plots that we just saw. So correlation, and here we're looking at middle finger length, goes in first, followed by pinky length. I like to always flag significant correlations, and we want to select for scatter plots. So here we go. We can see this is I edited it a bit for the axes, but we can see we have pinky length on our x-axis and middle length on our y-axis, and here is our graph. It may look a little bit different because it's a little stretched different, but I promise you it's the same one as right here. So here we have our correlation. We can see, again, this is a positive correlation. It's going up, which is also reflective of that slope. And we want to look at our Pearson correlation table to identify our Pearson's R value, which will help us identify how strong this correlation is. Really, we did the center, now we want to summarize the spread. So what is the correlation coefficient for the model? So this is going to come from right here. Pearson's R is 0.734. So R equals 0.734. What is the strength of the relationship using Cohen's interpretation of effect size? Well, I don't recall if we've done this one yet, but if we haven't, it is coming up in probably our next classwork. Let me see. Let's see if we can just Google this quickly instead of finding the right classwork. Cohen's Cohen's R effect size. So, effect size guidelines, since coming from an academic source, that looks good. So typically, We use the guidelines of 0.1, 0.3, and 0.5 as minimum cutoffs for small, medium, and large effect sizes. And we're going to get more into this, like I said, in a coming classwork if we haven't covered this yet. So based on this, we look at this 0.734. Is it bigger than 0.1? Yes, so it is at least a small effect size. Is it bigger than 0.3? Yes, at least a medium effect size. Is it bigger than 0.5? Yes, 0.7 is bigger than 0.5. So in this case, we actually are seeing a very large effect size. So on our strength, what this means is if it's a large effect size, that means it corresponds to a strong correlation. Right? Those points are pretty close to that line. It's a pretty strong correlation. If the points were really spread out, we would see a much weaker correlation. What direction is this going? As we mentioned, it's going up to the right. As the x gets higher, what happens to the y? It also gets higher. So this represents a positive relationship. Now on this r squared part, we're going to have to come back up to our regression model. In our model summary, this is where we'll see, again, we're looking at this H1 model. We want the model with pinky length in it. So if you follow this H1, what is the R that we see? 0.734. Interesting. Did we just see that? Yep, R is 0.734. It's the same R in this case because we only have one independent variable, so that R is going to be the same. It's just the correlation. The R squared is, well, let's take that 0.734 and multiply it by itself, and we get 0.538, which is exactly what we see right here, 0.538. So what this is doing is it's saying, okay, looking at this correlation, if we want to quantify how well our model is accounting for the differences that we see in middle finger length, we're going to refer to R squared for that. So let's see if it will let me copy this. No. Okay, well, R squared tells us how well our model explains the variability we see in the dependent variable. So in this case, R squared shows that our pinky model explained approximately, I'm going to think of this as a percent here, 0.538. And if you struggle in how you get a percent by that, it's always times 100%. So 53.8% or 53.9%. Okay? So it accounts for approximately 53.8% of the variation we see in middle finger lengths. Variation in middle finger lengths. So, in other words, of all the things that contribute to people having different lengths of middle fingers, if we were to look at pinkies, we can account for about 54% of that variation that we see by looking at what happens to their pinky. So this means that it doesn't exactly help us predict, right? It's not predicting every time, but over 50% is actually really, really good. This represents a very strong correlation. It's explaining a lot of the variability that we see. This means that approximately, right, if this is 54%, then that means that approximately 46% is not being accounted for by our model. And again, this is how much is this helping us to explain why we see those differences in our dependent variable. So at this point, I could do a basic reporting of kind of what I see in my model here. Right? So I might say that result, so maybe yeah, results of a linear regression analysis indicated that pinky length, and I can see here it was significant, so I'm going to go ahead and say significantly, but I'm not expecting you to necessarily get that part, right? So maybe we'll leave that out. So indicate that pinky length, maybe we'll change it this way, indicated that a model including pinky length explained approximately 53.8% of variability in middle finger length. And then we can say, and I really wish, I thought that I had set this so that it would wrap, but I guess not. So the equation for predicting middle finger length based on pinky finger length is y equals 45.40 plus 0.57x. You might also include the mean and standard deviation. But again, I'm just really looking for you to draw some sort of conclusions here, right? So we see that at that pinky length helps predict middle finger length to a high degree, and we see middle fingers increase by about 0.57 millimeters for each millimeter increase in pinky length. Now we'll go ahead and try to edit this and save this so I can share out that full version. And again, I'm just looking for your words. My words are obviously a lot different because I'm more experienced with this. But hopefully that gives you a better understanding of how we use regression analysis and correlation analysis to, again, help us model the relationship between two continuous variables or two quantitative variables.